So that's the chi-square test. And I want to do, let's see, we're going to do 2 more examples. We're actually going to skip this one. This says to do a z-test. I don't want to do another z-test. We've already done a bunch of them. So 1b, we can skip. Let's do the next 2. So example 2, I like this one. This one, actually, these are all going to be goodness of fit tests. And this one right away is about astrological signs. Do astrological signs affect your success in college? And I have 12 signs, so I actually have 12 observed values right away. 12 observed values. So it says a large Midwestern university looked at the astrological signs and GPAs of their top 240 students. They wanted to see, like, were their smartest students, were most of them in one specific sign, or was it an even distribution? So it says formulate your null and alternative hypothesis, find chi-squared, degrees of freedom, find the p-value. So let's do most of the steps, but so let's do the first one, actually. Let's do the first step. The first step is to state the null. So the null is the boring one that says our sign doesn't affect success. Your sign has nothing to do with your success. So sign does not affect success. In other words, our observed data fits the model. The model of just there's no relationship between your sign and your success. So observed data fits the model. And then the alternative is what people were trying to test. This was a study because people thought, I think your sign does affect your success. So the alternative is exactly that. Sign does affect success in college. Okay, and then for our second step to draw the box, this is more like a survey, right? We're picking people and asking them what's their sign. So we can think of the null box as having, for college students, having thousands of tickets, each with a sign. Each with a zodiac sign. And we're assuming the null is true. So we're assuming the sign doesn't affect their success. So we're assuming there's an equal number of each of the signs. And then we would draw 240 times to get our sample. 240 times without replacement. Right, so that's the null box, assuming the null hypothesis is true. There's an equal number of each. I'll say equal number of each sign in the whole population. We picked our top 240 students, so they should have equal number of signs as well. So that looks good. Step 3 is to calculate our test statistic, which is chi-squared. And so I'm going to use the table. Just like with conditional probability, I like the tables because it helped. Same with the chi-squared test statistic. We'll give you guys a table if you want to use it. You don't have to use it if you don't want to, but I think it's helpful because the very last cell is going to be your chi-squared. So my observed values are going to be given, which they are. My expected values are going to be based on the null. And then I can go ahead and fill in the chart. So I'm going to have you guys fill in this chart. I'm going to actually put up our very first iClicker question, which is about the expected values. So if you had to go about filling in your expected values, what would you put? And if you don't know, maybe don't fill out the rest of the chart just yet. But I want you guys to answer this question. Do you think all the expected values are going to be the same? or should they be different? So our observed values were definitely different, but what do we fill in for the expected? So think about that for a minute, and then we'll take a look. And I guess regardless of what you pick for this, try and think about what do you think. If you think they're all different, then what do you put for each one? If you think they're all the same, what do you put for each one as well? Okay, I'm going to stop. I think everyone's pretty much responded. So are they the same or are they different? So remember, expected values are based on the null, and the null says, good, that they're the same. That looks good. So they should all be the same. We should expect, if there's no relationship between sign and success, we should expect that all of these are exactly the same. So if we take all 240 students and divide them by the 12 signs, there should be about 20 students in each category. And we're kind of close. Like for Virgo, we got exactly 20. We observed exactly what we expected, but for some of them we're a little off. So the question is, as a whole list, are these differences big or not? Or could they be due to chance? Because the probability we get exactly 20 for every single group is pretty low. But how far off are we? So all the expecteds are the same. So it's just like the last one. So basically I'm just going to take all of these observed, 18 minus 20, negative 2, observed minus expected. I should get 0 as my sum. And I do, let's see. Five, 0. Something like that. And because I get 0, that's not super helpful on determining if my list is big or not. So I'm going to square all of these. So the negatives go away, 4, 1, 64, etc. And for this second to last column, I'm actually going to sum them because all of my expecteds are the same. So like I could take all of these numbers and put them over 20 if I wanted to and add all of them up. Or I could just say when I add all of them up, I get 254. And so I have that common denominator of 20. So I can go straight from here to here. So 254 over 20 gives me 12.7 as chi-squared. I get literally the same thing if I just put them with the denominator in the last column. But remember, for here, we only want to sum when all the expecteds are the same. So on the homework, you'll see sometimes we just have like an X right there because the sum isn't going to tell us anything. So the very last example we do, I'll do one where the expecteds are different so we could see when would that ever be the case. But so I found chi-squared. It was 12.7. My degrees of freedom is just the number of categories minus 1. So 12 minus 1 is 11. And this is going to help me find my p-value. So my very last two steps are to find my p-value and then state my conclusion. So we can, I guess, get practice using the chi-square table again. So I'm going to need 11 degrees of freedom and then 12.7. So I'll go to that same one on page 230 something, 231. And now this time I have 11 degrees of freedom. So degrees of freedom is 11. And my chi-square was 12, what was it, 12.7? Yeah, 12.7. So here's 12.9. That's really close. But I guess 12.7 is a little bit, they get bigger as I go this way. So 12.7 is going to be like right here, like really, really close to 12.9. So my p-value is about 30%. It's going to be a little bit bigger than 30%, which is big. Not less than 5 at least. So here, I'm going to say my p-value is bigger than 30%. Just slightly bigger than 30%. So that means the probability of getting these numbers from a population where your sign doesn't affect your success is about 30%. So we're saying that's a big enough probability that we're going to say, this is probably true. Your sign doesn't affect your success. We're not going to reject our null. So my conclusion is that P is not less than 5%, so we do not reject the null. And so we wrote down our null, sign does not affect success, so there's evidence of that. We're not rejecting it. And I guess just again, that whole idea of accepting the null, statisticians don't like when you say that, so you'll notice I always phrase it as we do not reject it, but you can think of it as saying there's evidence of the null. So I can even say there's evidence that your sign does not affect success in college. Does not. I'm running out of room. Does not affect success in college. Maybe they should do another study and see if it affects your success later in life. But those two examples we did, they both had, the model was that there was an equal number of people in each category. So I want to do one more example where that's not the case, because that is not always the case. But I guess any questions so far? Okay. So our last one. This is another going to be a chi-square test for goodness of fit. We can see exactly why. It says a town has, so this is what they're telling us. The town has 50% Christian, 30% Jewish, and 20% Muslim children. So that's what's in the town. That's what's in the whole population. If they tell you those percentages, then that is going to be our model. That's going to be our null. Our null is that, okay, then whatever we do with that population, that's what we should get. It says 100 children were chosen at random to participate in a community project. So my N is 100. And of the 100, we had 50 were Christian, 40 were Jewish, and 10 were Muslim. So we were just slightly off what we expected. This is what I observed. The model is what I expect. Could this have been a random sample? Because if it was a random sample, I should get exactly this within just a little bit of error. So it says, do a hypothesis test. And I know this is a goodness of fit test because I have 50 as an observed value, 40 as an observed value, and 10. So there's more than 2. So I can't do a z-test, I can't do a t-test. So if the model, if it said the town has an equal number of Christian, Jewish, and Muslim kids, then my expecteds would be equal, but it doesn't. It says the percentages are different. So let's do our test. So step 1 is to state my null, which is just that. I'm just going to say short and sweet, the observed data fits the model. The differences that we saw are due to chance. This was a random sample. Multiple ways to say that. The alternative, HA, is that the observed data does not fit the model, fit the population model. In other words, the sample was not random. If it truly was random, then we should have gotten closer to what we expected. So step 1, Done. Step 1, pretty much always the same. Step 2 for our null box, this is definitely more like a survey, right? We're surveying, we're picking kids and asking them, are they Christian, Jewish, or Muslim? So my box is going to assume the null is true. The data fits the model. So it's going to assume that we have 50% Christian, 30% Jewish, and 20% Muslim children. So these percentages that they gave me, I'm going to assume those are true for, this is a town, so for the thousands of children. So there's going to be thousands of tickets. And this is what I'd expect. Okay, so for the hypothesis test, your box is always going to assume your null hypothesis is true. And you can remember, the null is dull. It's the boring one. There's nothing weird going on. This is a random sample. That's what they claim. So that's what it is. So when I draw out of this box, when I draw 100 times without replacement for surveys, I don't want to pick the same kid twice to be in my sample to participate in this project. You probably need all the kids you can get. I'd expect to get these percentages, but I actually didn't. I got a little bit different. So my step 3 is to, this one doesn't give me a table, which is kind of annoying. I have to draw my own, but you guys will get a table. So step 3 is to calculate my test statistic chi-squared. Because I want to know, are these numbers different than what I observed? So the very first, let's see, how do I make this table? I guess, let's see, how would I do it? I would say there's Christian, Jewish, and Muslim children. And then the last row is always going to be the sum. Oops, there we go. And we'll start off with what we're given. So our observed values, if I go back to the original question, it says, of the 100 children we observed, 50 were Christian, 40 were Jewish, and 10 were Muslim. So out of the 100 kids, that's what I got. But I expected something else. I expected what they told me was in the population. So I expected 50% of the kids to be Christian. I guess I observed exactly what I expected, right? 50% of 100 is 50. So that's good. That's a good sign. If all of your observed and expecteds are equal, you don't even need to do a hypothesis test, because then you know that you observed what you expected. You don't need to test it. And then 30% I expected to be Jewish, so this was a little bit different. 30% of 100 is 30. And then for the Muslim children, I expected 20. 20% of 100 is 20. Oops. There. Yeah, 20%. That's what I expected. So I expected what they told me was in the population. I didn't actually get that. And the next column, if we look at, you guys will be given this on the exam, but the next column is actually observed minus expected. So 50 minus 50 is 0. 40 minus 30 is 10. 10 minus 20 is negative 10. So this sum should be 0, and we do see that, so that's good. So in order to get rid of those negatives, I'm actually going to do observed minus expected squared is my next column. So 0 squared is 0. We've done that one. 10 squared is 100. Negative 10 squared is also 100. And then if I sum those, I get 200. But here the sum isn't really going to help me, so I'm actually not even going to. You could sum it if you want. It wouldn't hurt, but it's not going to tell me anything. Instead, I'm going to have to actually use the formula, which is observed minus expected squared over expected. So I'm just making the same table that we had before. So same as this up here. I'm just making the exact same thing. But like I said, on the final, you guys will have the table, you'll have the formula, you will be good to go. So let's see. So observed minus expected squared was 0 over the expected was 50. So 0 over 50 is 0. And then 100 is observed minus expected squared over 30 was my expected. So that's 3.33. And then here I have 100 over my expected was 20, which is 5. And then the sum, this last cell is always going to be your chi-squared. It's the sum of the observed minus expected squared over the expected. So 0 plus 3.33 plus 5 gives me 8.33. So there's my test statistic. My degrees of freedom is just the number of categories minus 1. So 3 minus 1 is 2. Right? Number of observed values minus 1, you could think of it as. And then the last 2 steps so I need to find the p-value, which is going to be, let's go ahead and check. Page 231. And then we'll state our conclusion. Our conclusion will be our last question, eye-clicker of the day. And then you guys will be good. But let's find our p-value first. So we had 3 observed values, 3 categories. 3 minus 1 is 2. Here's 2. Our chi-square statistic was 8.33. So it looks like, again, 8.33 is between 5.99 and 9.21. So our p-value is also between 1 and 5%. P-value is between 1% and 5%. So our very last step is to state our conclusion. So our p is less than 5, right? P is less than 5. So we reject the null. And I'm going to put up 2 options. I want you guys to pick which one's right. What does that mean for this? Was it a random sample? Is there evidence of a random sample? So here it is. Last question. We'll do some more examples on Tuesday, but go ahead and pick. Is it evidence it was a random sample or not? We're rejecting our null. So what does that mean? And I'll see you guys on Tuesday. Have a good weekend. If anyone has any questions, I'll be up in the front for a bit.